the Wigner function for the Fock states. If you recall, the Wigner function was given as W of alpha equal to 1 by pi square integration d2 gamma e raised to alpha gamma star minus gamma alpha star psi d cap gamma psi, where d cap is the displacement operator. Now, as we want to find the expression for the Wigner function for the Fock states, psi can be replaced by n, that is the number state or the Fock state. So to calculate the expression for W alpha, we need to first find this particular quantity. So let us find it. So psi d cap gamma psi is equal to n d cap gamma n for our case. And this can be written as e raised to gamma a dagger minus gamma star a into n. We just replaced d cap by its explicit definition. Now that we know that e raised to a cap plus b cap is equal to e raised to a cap, e raised to b cap, e raised to minus mod of a cap comma b cap by 2, and the commutator a comma a dagger is equal to 1. We use these both, and we can write n d cap n equal to e raised to minus half mod of gamma square n e raised to gamma a dagger e raised to minus gamma star a n. Now e raised to minus gamma star a is equal to 1 minus gamma star a plus gamma star square a square by 2 factorial, and so on. This can be written in the shorthand notation as m equal to 0 to infinity minus 1 raised to m gamma star raised to m divided by m factorial a cap raised to m. Similarly, e raised to gamma a dagger can be written as summation L equal to 0 to infinity gamma raised to L divided by L factorial into a dagger raised to L. So we substitute these both here. So n d cap n is e raised to minus half mod of gamma square summation m comma L equal to 0 to infinity minus 1 raised to m gamma star raised to m gamma raised to L divided by m factorial into L factorial n times a dagger raised to L a raised to m n. Okay, so this particular quantity is non-zero only when L is equal to m. Let me show you an example. So let's say L is equal to 1 and m is equal to 2. Then this thing is equal to n into a dagger a square n. This will give me root of n into root of n minus 1, and when this acts here it will give me root of n plus 1, and this will be equal to, let me just write it down, root of n minus 1 into root of n plus 1 n plus 1 n minus 2. Now you see that this, according to orthogonality, this is equal to 0, so this entire thing will be 0. These things are non-zero only when this particular expression is non-zero only when L is equal to m. So we can replace all L's with m. So I will just do that here. So this becomes equal to m and m. So I replace them, and I can write this thing as this entire thing as minus mod of gamma square raised to m, and this as m factorial square. Now let us calculate this particular quantity. For m equal to 0, this quantity is equal to a dagger raised to 0, a raised to 0, n, and it is equal to 1. For m equal to 1, this is n, a dagger a, n, which is equal to n. For m is equal to 2, this quantity is n, a dagger square, a square, n. Let us first act this here. Let us write this in this manner: a dagger, a dagger, a. So let us act this here and this here first. So this is equal to root of n square, n minus 1, a dagger a, n minus 1. And then again, when this operators will act, this will give me root of n square into root of n minus 1 square, which is equal to n into n minus 1. So when we have m, this becomes a dagger raised to m, a raised to m, n is equal to n into n minus 1 into up to n minus m minus 1. Okay, so I can substitute this here, and this is nothing but equal to n factorial divided by n minus m factorial. So I can substitute this as n factorial divided by n minus m factorial here. And I can take this square term from m factorial term from here and put it here. So this is now equal something like n cm, and I can write this entire thing as n cm. But this is nothing but a Legore polynomial. So Legore polynomials are given as such: L0 mod of L0x equal to 1, L1x is equal to L1x is equal to minus x plus 1, L2 of x is equal to half into x square minus 4x plus 2, and so on. I call this thing as a Legore polynomial. So in short, n d cap n reduces to minus half mod of gamma square into ln of mod of gamma square. So now that we have got this expression, we can substitute it here in the definition of the Wigner function. So my Wigner function for the Fock state becomes Wn alpha. I will write n here to denote that it is for the Fock state. So it is equal to 1 by pi square d2 gamma e raised to alpha gamma star minus gamma alpha star e raised to minus mod of gamma square by 2 into ln of mod of gamma square. This is in general for a Fock state. Now we still have this integration term inside, right? So in general, let us try to remove it. So let us start with the vacuum state. For n is equal to 0, W0 alpha is equal to 1 by pi square integration d2 gamma e raised to alpha gamma star minus gamma alpha star into e raised to minus mod of gamma square by 2. We considered L of 0, L0 of mod of gamma square is equal to 1. So that is why it is not written there. Now this is the complex integration in the plane, complex plane, where gamma is a complex number. And we had defined this gamma in the previous two videos. Yeah. So this we can write it as 1 by pi square integration dx dy by 4. We have done this in the previous videos, and this as alpha x alpha dash x I into alpha mod alpha double dash y e raised to x square by 4 plus y square by 4 divided by 2. I just used our definitions of gamma, which we have derived earlier. And now this is equal to 1 by 4 pi square integration dx e raised to I alpha prime x e raised to minus x square by 4 by 2 into integration dy e raised to I double prime y e raised to minus y square by 4 by 2. So this is like Fourier transform of Gaussian function. This is also same Fourier transform of a Gaussian function. So this is equal to 1 by 4 pi squared into 2 root 2 pi e raised to minus 2 alpha square, and this is 2 root 2 pi e raised to minus 2 alpha double prime square. You can look up what you get as the Fourier transform of a Gaussian. In fact, it's a Gaussian. That is what I have used here. So this can be written now as 2 by pi e raised to minus 2 alpha prime square plus alpha double prime square, and hence w0 alpha, this was nothing but w0 alpha. This w0 alpha is 2 by pi e raised to minus 2 mod square. This is the final expression of the Wigner function. You can see that it is nothing but a Gaussian. I'll plot this very soon. And if I use this uh, expression that alpha is expectation value of x I p and alpha star is x, I will just write them as x and p. Okay, if we have already seen this earlier, and I'm not going to explain why it is so this can be written as w0 x comma p. In the xp uh, variables, I can just replace mod of alpha square here. So this can be written as minus 2 mod of x plus ip mod square, which is equal to 2 by pi e raised to minus 2 x square plus p square. So this is like a two-dimensional Gaussian function. And when we will plot it, we can explicitly see that it is like a two-dimensional Gaussian function. Now let us find the Wigner function for n equal to 1. So w1 alpha now is equal to 1 by pi square integration d2 gamma e raised to alpha gamma star minus gamma alpha star times e raised to minus mod of gamma square by 2 into 1 minus mod of gamma square. This is nothing but the Lagrange polynomial for n equal to 1. uh, I leave the calculation on you, and I give you the result that W1 alpha is minus 2 by pi e raised to minus 2 mod of alpha square times 1 minus 4 mod of alpha square. So we have a Gaussian multiplied by this extra term. And replace alpha by x and p, then this is equal to minus 2 by pi e raised to minus 2 mod of x square plus p square times 1 minus 4 of x square plus p square. You see that in both cases we have a negative sign that shows that the Wigner function is can be negative. Moreover, we will also see that it is not always normalizable. Now let us write the general expression for the Wigner functions for the Fock state, looking at these previous two expressions. From these previous two expressions, this is for n is equal to 0, n equal to 0, n equal to 1, and this is also equal to n equal to 1. So Wn alpha is equal to 2 by pi minus 1 raised to n e raised to minus 2 mod of alpha square ln of 4 times mod of alpha square. This is how you will see your Wigner functions for a general Fock state. And Wn in the xp basis is 2 by pi e raised to minus 1 raised to n e raised to minus 2 x square plus p square into ln of 4 times x square plus p square. This is a general expression for the Wigner function in the alpha and xp basis. Now we can see a few properties from here, that the maximum value of the Wigner function is 2 by pi, and the minimum value of the Wigner function for the Fock state is minus 2 by pi if the Gaussians and the Lagrange polynomials are normalized. But we can see that in any case, this is never, the maximum is never equal to 1. And we can also see that Wnxp is a symmetric function. That is, the Wigner function of the Fock states is always symmetric because the Gaussian and the Lagrange polynomials are always symmetric. So a product of symmetric functions is a symmetric function, and hence the Wigner functions. We had seen that W0 x comma p was equal to 2 by pi e raised to minus 2 mod of 2x square plus p square. Now if I plot this with x, this being x and this being p, if I plot this function for the vacuum state, it will be centered at the origin, and it will look like a 2D Gaussian like this. Now the projection of this particular uh, 2D Gaussian on the x-axis will give me a marginal probability distribution function p of x, which is equal to integration w0 x comma p dp. In the same way, the projection of this 2D Gaussian on the y-axis, or the shadow, we can also call it in that way, will give me the probability distribution function of w0 x comma p dx. So it's a marginal probability distribution functions. These are, and they represent the probability distribution functions of the state for x and p respectively. Now, if I create a contour plot, I can see that the Wigner function is symmetric and the spread is given by delta a, delta p, and delta x. It's proportional to them, the spread of this Wigner function. Okay, now if we move on and plot the Wigner function for n equal to 1 state, then this is equal to -1 or -2 by pi, -2 by pi e raised to -2 mod of x square plus p square, the Gaussian, times this Lagrange polynomial 1 minus 4 times mod of 1 minus 4 times x square plus p square. So this gives me this particular function, this plot here, where x-axis represents mod of x and y-axis represents mod of p. Sorry, expectation value of x and expectation value of p. And we see that this is negative. It goes in the negative direction, as we had said that it is a quantitative probability distribution function. And moreover, it is not normalizable, and as I said, it will be centered at origin. And if I create a contour plot of x and p, I will see that again it is symmetric. However, the spread is larger, as we had seen in the previous videos, that delta x n and delta pn was equal to root of h bar into n plus half, if you recall. Yeah. So as n increases, the spread increases. In fact, if I plot the first, second, third, fourth, n equal to 0, n equal to 1, n equal to 2, 3, 4, 5, the Wigner functions for them, they will look like this, as shown.